In this lecture we will discuss types. Types are important whenever we discuss programming languages. And here we will find out how we deal with types in Scheme. I have two functions, factorial and a list function that returns every second element of a list. So, can we see any types in these two functions? No, not really. We have the formal parameter n of the factorial function. We cannot see if it's supposed to be an integer, because we do not use static types in Scheme, and we cannot see either if factorial returns an integer or another type. The same is true for every second element. Well, from the name we can guess that this is a list, but there's no static information about the first formal parameter being a list. So, in general, why do we have types? First, for readability purposes. So, does that apply to Scheme here? No, not really, because the types are missing from source program. Another reason for having types is efficiency. We are supposing that we can generate better code in case we have types. So that does not apply for Scheme either, because we cannot benefit from having type information in our program. The last important thing about types is correctness. So if we have types if we have static types, we can find errors early. So what about Scheme programs? Do we find errors early? No, not really. In Scheme we deal with types at runtime. Every piece of data has a type. So when we are running the program, we can exercise the type of n. So we can simply ask for the type of n in case we care. Here we assume that it's numeric, but we could in fact ask and ensure at runtime that n is numeric. And I'll come back to that in a little while. So now that we are in a read-eval print loop, and I'll illustrate various aspects of types in the Scheme programming language. So let us define factorial and every second element, which we have just discussed. So we enter them into our read-eval print loop. Here we are. And then we can try them out. I can call factorial on an integer, and I get the expected result. But what happens if I apply factorial on a non-number, for example, on a list? Well, I get an error. I don't get any errors at before runtime, but I get a runtime error. So the problem is that this equality does not apply on list. So therefore I get the runtime error. Let us try every second element on a list, and I get every second element as expected. But what happens if I use it on Boolean false, for example? Well, there's nothing to guard us here, so it's this cutter that fails. Cutter cannot be used on Boolean values. The problem is identified at runtime, and here is the runtime error. That's a game we are playing in Scheme. Now let us walk through the different types available in Scheme, and we start with integers. So is an integer a number? Well, it is. We use the number question mark predicate. For each type available, there is such a predicate, and we get Boolean true. Is it an integer? Yes, it is. Let us let us try to calculate 50 factorial, and this is quite a large number. Scheme is strong to deal with large numbers, as we can see here, and Scheme also handles rational numbers or fractions. So is 50 a rational? Yes. Is this number an integer? No, it is not. We should also try this one, of course. Is this fraction a rational? Yes, of course it is. Is this a real number? Yes, rational numbers are conceptually also real numbers, so Scheme got it right. Scheme is quite strong when it comes to numeric types. Here we have real numbers, as they're called in Scheme, or floating point numbers. So a floating point number, a real number, is a number. It's a real, but it's not an integer. If you look at the details of factorial, nothing prevents us from passing a real number to factorial. And we get a real number back with exponential notation, as we see here. Say it's a large one. And indeed, the result is a real number. If we apply factorial on 500, well, we get overflow in reals, so we get an infinite number as result, which is close to being true. Scheme can handle complex numbers as well. So square of -9 is this complex number. Complex numbers are not real, but they are of course complex. Okay, so that was the numeric types. Let's now face the Boolean type, and there are two Boolean values, and we have seen them already, true and false, which are self-evaluating, and these are Booleans, and these are the only Boolean values. So 0, for example, is not a Boolean in Scheme, and that's nice and natural. Now characters. The character notation in Scheme is a little bit odd. So this is notation for lowercase a and uppercase a. A is a character. We can convert characters to integers, but this integer is not a character. There are some special characters, for example space and new line, which are named. Next, symbols. Symbols are unique strings, so there's only one instance of the symbol A, whereas there may be several instances of a given string. That's the design in Scheme. There are many other alternatives, as we know from other programming languages. So this was a symbol, and it is indeed a symbol as recognized by the simple question mark predicate. A text string is not a symbol. So we get Boolean false when we apply the simple predicate on a text string. So here is a text string with a single letter, and text strings are notated the way we are used to, in double quotes. And this is a string, and this is another string, slightly longer. In Scheme we also have arrays. They are called vectors, and they have this funny notation with a number sign in front of a pair of parentheses where we have the elements. So that's a direct way to notate a vector, and it is indeed a vector as recognized by the vector question mark predicate. But there are other ways to construct a vector. So there is a function called vector which gives the same result, and there is a make vector. So let us make a vector of 10 elements, each being the integer 5. So the length of this vector is 10, so there are 10 elements, and we can access the elements of a vector by means of a function called vector ref, corresponding to subscripting. So the third element in this vector is d, because the first one is numbered 0, as we are used to. If we index out of range, we get a runtime error. That's also quite similar to most other programming languages. It's a runtime error in Scheme, it's a runtime error in C and Java and so on. Okay, lists are very important in Lisp and Scheme. So here's a list. It is a list. It's a proper list, and it can be constructed by using this function as well. This is not a list. It is an improper list. It is an S expression. So we can just try it out. Is it a list? No, it is not. But it is a pair. It is an S expression. Okay, the last type we will deal with is functions. They are in fact called procedures in Scheme. So this is an example of a function. It's a lambda expression, and when we evaluate the lambda expression, we get a function, and the printed representation of functions are, well, they're not printable. So we just get this result back. Well, we have some procedure, it's called. So this is the function that adds 1 to its parameter. So the parameter better have to be numeric. This is the identity functions. There's also a predicate that identifies functions, and it's called procedure. Okay, so now we have walked through most of the types which exists in Scheme. We have seen how to deal with concrete values in these types, and we have seen that there are predicates that identifies all the types at runtime. Scheme does not use static typing. Every piece of data has a type, and these types exist at runtime. We can test for these types. If we do not test for the types and we apply wrong functions on the type, we get runtime errors. That's the game we are playing in Scheme.